And what this section of slides is about, don't write code to begin with. Write a loop invariant to begin with, and then have the loop invariant design your code for you. All right. So I, your boss, give you the precondition is that I is an integer, and I give you, oh, see, that shouldn't have, see, I was just making those slides. This shouldn't have come out yet, right? But what's our post condition? Our post condition is that we have the sum of all these I objects, right? So what do we want our loop invariant to be? Here I've added a discussion about it, right? You could say each iteration adds a new object, right? But that's an action, not a picture, right? And this is a threat. Don't fight me on this because I will fail you, right? All right, so now what is a loop invariant? It says what needs to be true in the middle of the computation, right? Well, let's think about it. The post condition says that I've added a bunch of objects together, right? And so what do I want in the middle of computation? Well, I've added some of them together, right? And it's going to be a prefix. I might as well do them in order. So it tells me I've added a prefix of them together. All right, so now we want to think about what our data structure is going to be. Well, I could use I to denote the index of the next object to add in, right? I'm at the top of the loop. I'm about to add in I. So that would tell me that I've already added I minus one of them, right? If I'm about to add I. Then what would my loop invariant be? Well, it would be that I've added the first I minus one of them together, right? Does that make sense? Now, another option is I could have I denote the number that I've added together, right? So then my loop invariant would be that I've added together the first I objects, right? And in that case, the next object to add in would be the I plus first, right? Now, you might ask, which of these should you do on a test? And I will say, I do not care what you do, this one or this one. I call it a matter of aesthetics, right? You want I to be, well, it could be what you've done so far. It could be the one to add in next, right? It's a matter of aesthetics. Now, why did I do this one? I did this one. Right? Why did I do this one? Because I was focused on making the loop invariant pretty, right? And you'll notice the code then gets a little ugly because you're adding in the I plus first, right? It would be perfectly reasonable to come over in here and say, I want my code to be pretty. I want to add in the ith object, right? And then that would mean I've done I minus one so far, right? Does it matter? No. Right here now, what am I saying? Which one of you does which loop invariant you write down here will change everything. It will change the code. It will change the right. But all that matters is that it's consistent. And you might say to yourself, why should I write down this loop invariant or that loop invariant if it doesn't matter? Well, what matters is that you're consistent. What does that mean? Is when you're establishing the loop invariant, when you're maintaining the loop invariant, when you're getting the post condition from the loop invariant, and all three of those, you need the same loop invariant. So I don't care which loop invariant you have, as long as it's the same, right? All right. So now you might say, well, why did I have a little s and a little I? Well, it's because I like to have notation that everybody understands. Right? And capital I is the input. Capital S is the output. S and I are my current data structure, right? When I say, what's my internal data structure? Well, remember I and S are, well, I is not going to change and S is going to happen until the end. And my internal data structure will be I and S, little I and S, right? And what does the loop invariant do? It tells me a relationship between I and S. It tells me a relationship between my data structure items, right? Does that make sense? Now you might say, well, you might be tempted to think about what range I has, right? Does it start at 0? Does it start at 1? Does it end at one of these things, right? You might worry about it. And that's when I realized that it was 5.2 and I stopped making slides, all right? But let me just tell you what the new slides would be is here I'm trying to say, don't think about that right now, all right? Right now, our task is jumping into the middle of the code, middle of the computation, and having our loop invariant and focused on maintaining the loop invariant. And the reason, and we don't want to worry about how we start or how we end right now, right? If you want a concrete value of I, well, let I be 5, right? It doesn't matter. It's somewhere in the middle. It's not the nuances at the beginning. It's not the nuances at the end, all right? And why?
Professor, sorry to cut you off. I just have a question. What's the difference between the capital S and the small s?
All right, let me finish my sentence.
Okay.
Why do I tell you not to worry about the beginning or the end? It's because you will have to worry about it at some point. But if you worry about the entire computation at once, you will crash, you'll panic, and you'll crash, and you'll burn, and you'll drown and fail the course, right? So the emphasis, what I'm trying to emphasize is be a Buddhist and clear your mind of all the worries of the world, and then just worry about one worry at a time, right? Remember, Patrick was last class, he even started to panic because he was worried about too many things at the same time, right? So I'm saying we're not going to worry about this right now. We will worry about it later. All right, so now somebody asked the difference between capital S and little s. Well, capital I is our input value, and little I is changing through our loop. And right now, see here, look at how I changed the loop invariant here. Capital I is bigger than little I, right? So here I've sum up to capital I is a longer sum than summing up to a little I. And so those are the difference between capital I and little I. And then capital S will be the sum up to capital I, and little s is the sum up to little I. And little s is our ongoing data structure, right? And capital S is reserved to use for the output, right? Does that answer your question?
Yes, thank you.
In English, would that kind of be saying like the loop invariant is that at every iteration of our loop, we've calculated like the partial sum up to a certain point?
Yeah.
That's what it is, right?
S and I, S is our partial sum, and I tells us little s is our partial sum, little I tells us how far we've gone.
Okay.
Right. And then we moved on to, well, what's our measure of progress? Well, just I alone is an obvious measure of progress. So how do you make progress? You just have to increase I, right? And what is our exit condition? That goes back to don't worry about it yet, right? Don't worry about it yet. You know, when I is big, you'll stop, right? Right now, it's not big enough, right? Does that make sense? In some ways, this example is so easy that you might think this is a dumb example. And the truth is the example that everybody crashed and burned was harder than this. But I went back to an easy example. So what I'm saying is, suppose in order to, you have to do two things in your iteration. You have to make progress and maintain the loop invariant, right? So people don't know how to do both at the same time. So what I'm saying is, do them separately. First, I'm standing here. I know the loop invariant is true. I'm on the path. So I'm going to make progress. All I need to do to make progress is to add 1 to I, right? So I add 1 to I, and that puts me up here, right? Is my loop invariant true now? No, I changed I didn't change S, right? The loop invariant is not true. So then, in order to make, now I have to reestablish the loop invariant, right? I'm going to now say, now, how do I come back to make the loop invariant true again, right? Does that make sense?
Yeah. So the I equals I plus 1 is the step to make the progress, and the S equals S plus I squared is how you maintain the loop invariant.
How you bring it back onto the path.
Okay.
Exactly. Like, so here we, yeah.
But see, that's where I get confused, because I would have just thought that S equals S plus I squared would be the loop invariant. I still don't understand how you came up with like the capital S and the lowercase s, and then the capital I and the lowercase I. I get like you. That's the only part that I don't understand. Like if I wouldn't have done that. I wouldn't have thought that if I just changed the letters, it would be the loop invariant.
All right, well, partly I want every letter to have a meaning that we know what it is, right? And so capital I is my input, and I'm going to leave capital I to mean my input. And then capital S is going to be my output, right? So I'm going to keep that letter to mean my output. And so now I'm on the inside of my loop, and I have some data structure. And what's my data structure going to be? Is going to have some I, and I'm going to have some S, right? And they're going to be changing, right? I know I'm going to be changing I and changing S. And so I gave them different letters, not to confuse them. It looks like I have different oranges too. Sometimes I can't tell the difference between the oranges, but that orange looks different than that orange. It's not supposed to be. But anyway, right? So that's why I said right? And then over here, right? So little s and little I are my internal variables within the loop, right? And then what does this say? This says more than that. When I'm at the top of the loop, my little variable s has value st. And when I go around, my little variable s has value st plus 1, right?
Yeah.
I'm giving names to everything so that we can talk about them, right? And now here, so this is what I said you're supposed to do on your test. You copy down, what does the loop invariant say at time t? Well, I said at time t, I have variables it and st, and loop invariant being true at time t, I just copy down the loop invariant with respect to the time t values, right? And then what does the code give me? Well, it gives me I'm not done. What does this give me? Well, we're going to have a bunch of code, but one of the code is I have to do this, right? So to do this, let's write down that into math, right? This tells me my new value of I compared to my old value of I, right? And then now, why are we doing all this? Is because we don't know what the code is yet. How can you prove code works when you don't even know what the code is, right? So I say, even if you're on an hour-and-a-half test, don't write up your solution in order. Somewhere above this, you're going to be telling me what your code is, but you don't know what your code is yet. So come down here and start proving your code works, right? We're going to start proving our code works here before we know what the code is, right? So we wrote these things down and we got stuck, right? So now let's start at this end and go backwards. What do we need to be true? What we need to be true is that the new value of s is the summed up to the new value of I squared, right? So this is what we want. This is what we have, right? So now we're going to do a little hand waving in between, right? So we're going to observe, oh, look at, this is what we want. And it seems pretty natural and this is what we have, right? What we want to do is make what we have look like what we want, right? And what we have is the sum up to this it. So this looks like we can break it into these two pieces, right? Now this sum up to here by this definition is ST, right? So now this is a proof. Only thing we're missing is what do we need? We need this to be true, right? No one's, we've proven already this equals, we've done this equals, right? Because this up here gives us that equals. How do I get that equals right there? Well, I haven't defined my new value of S yet. Let's now go in and say, what do I want my code to do? I want my code to make my new value of S be my old value of S plus the new value of I squared, right? I write this in here because that's what I need to prove it, right? Does that make sense? All right, so now look at, we finished the proof. Now, after we haven't even come up with this code yet, right? We came up with the math version of the code. Now we have to take the math version of the code and translate it into actual code, right? So how do we translate it into actual code, right? Now we translate the math into code. Well, does this do the trick?
Yeah, does do the trick, yeah.
Everybody says it does the trick?
Yes,
Come on,
'cause-
guys. Didn't you watch the video?
yes,
Mhm.
we did, yeah. So yeah, we
So-
can see it does the trick. Because we're adding the,
It doesn't do
add-
the trick.
yeah,
Why?
we're
Because
add,
at the top of the loop, S is summed up to my current value of I. So do I want to add on my current value of I to S? No. I need to add on the new value of I to S, right? This is adding the old value of I to S, right? So this is why you need a loop invariant, because if I knew the loop invariant was told me that S is summed up to I, then what do I need to add on next? I need to add I plus 1 on next, right? So this code doesn't add on I plus 1 next, it adds on I next. So that's wrong. How do you fix it? That's one way to fix it. Then we can do the next steps, right? We can say, now we say, hey, TA, I'm doing this one. And why do you want to write it so bold, what you're doing? One, to make sure your TA knows what you're doing. But you know, if I'm marking it, I know the order in which I want to read it. You don't know the order I'm going to read it. So you tell me where you do each step, and I'm going to zoom in to the step that I care about, right? So here's the post condition. You tell me, you write this down. This is what I have to, what I'm going to do next, right? So let's write it down. So here's the invariant, right? What do I get from the invariant? That's my loop invariant, right? Here's my exit condition, right? So remember, I wrote in exit conditions before, but here I'm writing in, I don't really know yet, right? Maybe I should go back and write, I don't really know yet on those previous things so that Patrick won't get upset about it, right? So here I'm saying I don't know. All right, so now what's my code do? Well, I don't know the code yet really either, right? So let's come up to the post condition. What's the post condition? My post condition is that capital S needs to be summed up to little I. Capital I, right? And so I compare these. I say, what do we need? Well, clearly I need capital S, you know, I need these to be the same, right? So I need little s and capital S to be the same, and I need little I and capital I to be the same, and then we're done. Right? Then we're, well, little I is our measure of progress. So when do you exit? You exit when you've made enough progress. So let's exit when little I equals capital I. Right? And what is capital S? Capital S is our output. So we have to have our math say that little s equals capital S, right? This is the code after the loop, right? Is going to tell us that math. So everybody agree that it follows that from this, I get this, right? Everybody see we just write down some obvious things, right? And so now, again, we have math and we need to produce this math into code, right? So everybody see what the exit condition is pretty straightforward. What's my code after the loop?
How did you figure out the exit condition again? Sorry, I missed that.
Well, I was here.
Yeah.
This is my loop invariant. This is my post condition. And I somehow, from this, I need this. What things would be true? What things do I need to be true for this to be this, to give me this? I just say, hey, what happens if I knew that? What happens if I knew those two things?
Oh, okay.
Right? If
Yeah.
I knew those two things, I would be done, right?
Yeah.
All right. So one of them is our measure of progress. So let's make that our exit condition, right? And one of them is producing our output, right? So let's make that to be your code after our loop, right? I mean, it sort of makes sense. When are you done? My loop invariant says I've summed up the little I. What do I need to do? I need to sum up the capital I. Every time little I gets bigger, so it's getting closer to capital I. When will I be done? Well, when I've summed up the capital I, will I be done? But I've summed up the little I. So if little I was capital I would be done, right? So now I have these math things and I need to turn them into code. Right? Everybody good?
Yeah.
Una. Hey, that's that. Surely you don't say that. How do you say your name?
My name?
Doesn't start with an X, eh? Oh. Anyway, how do I turn math into code? Anybody want to tell me what? Right. So here's our loop invariant, right? It's the code that happens right here after the loop, right? From the loop invariant and the exit condition, I need to get the post condition. What code should I put there?
S equals capital S equals lowercase s.
Yeah, so you turn it around. Why did you turn it around?
Sorry,
code.
aren't we returning uppercase? Like, sorry, isn't the post condition saying that uppercase S needs to be the total sum?
Yeah, for sure. I'm just messing with you, buddy.
Oh, okay.
Right. So here's I could put that in there, right? But no. What code makes this? Code makes the I equal I true?
The
right?
exit condition.
It's the X condition that makes it true, right? Right. Now you'll note some people like while statements. I personally like loop statements. Exit. I want to be told when you're going to exit, while the while tells me when you're going to not exit, right? So you could flip it around to a while if you wanted, but you can see mine is more mathematically friendly. All right, so now I keep having to move your faces. Your faces get on top of my screen. All right, so right, so say, this, right? So this is just saying equals, not equals is a little scary for me. The reason it's scary is because, right, maybe I skip it, right? If I equals, if it keeps going up by an even amount, then you might not actually be equal. So that's why I like less than versus greater than or greater or equal to. It makes me feel a little bit more secure that if I pass it, I will exit. But let's not worry about that too much. All right. So what code are we giving in there? Right. This is what Patrick said. Capital S equals little s, and I got it turned around here. Right. Now, why did I turn it around? Is because here is a math statement. Little s equals capital S and capital S equals little s are the same. Why did I write it this way? Was to mess with you. And why does it need to be this way? It's because we have little s and we want to find big S, right? So everybody good? Everybody good with that?
Yes, but I want to say one thing is that before I was confused by you're saying math statement switch to the codes, but then after I read all of your materials, I found that maybe we can understand in another way, and that is what is making the measure progress. It is our little I. So since it is little I making progress at each step, so it should show up in exit condition. He should
Right.
know when he should stop his work. So that's why we let little I equals to the capital I.
Yeah, exactly. When I exit, this is what I want to be true when I get down to the post condition, right? I need this to be true. How do I make them true? Well, I'm making this one true by having it be my exit condition. And I'm making this one true by, well, I have a value for little s. I don't have a value for capital S. So set capital S to be little s, right? I didn't understand what you didn't understand. It sounded to me like you understand everything. I didn't get a question.
Oh, no, I'm not saying a question.
All right. Yeah, I think you get it. Are you good here?
Yes, I'm good here. Because in your video, someone else said that he's confused by the math statement and the code switch.
Right, exactly. And Patrick wasn't confused, right? Patrick knew to switch it, right? And why did I put it in there? I put it in to confuse people, right? So that there might be a little, I wanted to show you a difference. I wanted my math statement and my code statement to be different so that you appreciated that I'm doing work here, turning math into code. There is some work, and the work is you have to switch it, right? Because this is a Boolean statement, right? This is a very different, this is a Boolean thing that says these two boxes have the same value. And this is code, which takes the objects, right? And I wanted everybody to appreciate. I wanted to draw attention to the fact that this and this are different objects, right?
I see.
The way I drew the attention to it is I switched it, right? So that it wouldn't just fly over you quickly. All right, so now we have to do this bit, right? So how do we do it? Well, sometimes people get nervous at the beginning. If I is 1, then clearly S is 1, right? I is 2, and then it's 5, right? That's pretty straightforward. If I is 0, if we have 0 elephants in the room, are they all pink, right? What does S need to be?
0.
0.
0. S needs to be 0 because we've gotten some up to, right? That's a 0. And partly the reason I know it's 0 is because how do I get from 1 to 5 is I add on 2 squared. How do I get from this number to this number? So I add on 1 squared, right? And this is 1, so that better be 0, right? So what's my initial code? There's code, right? And we're done.